In this lesson, you will learn how to solve compound inequalities, graph their solutions on a number line, and write them in interval notation. We'll look at several cases, including when there's no solution at all and when the solution is all real numbers. A compound inequality is simply two single inequalities combined into one statement using the word and or the word or. So, the first step in solving a compound inequality is to solve each single inequality separately. Remember, the goal for each is to get x by itself using opposite operations, just as you always do. Alright, let's start with the first inequality. To get x by itself, subtract 6 from both sides. On the left, 6 minus 6 is 0, they cancel out, leaving just x. On the right, 7 minus 6 gives us 1. So the solution to the first inequality is x is greater than or equal to 1. Great, now let's solve the second inequality. First, isolate 3x by adding 5 to both sides. On the left, the 5's cancel out, leaving 3x. On the right, we get 15. Now divide both sides by 3 to isolate x. The 3's cancel, leaving x by itself. And 15 divided by 3 is 5, right? So the solution to the second inequality is x is less than 5. Now that we've solved both inequalities separately, the next step is to graph their solutions on a number line. X is greater than or equal to 1 means x can be any number bigger than 1, including 1 itself. To show 1 is included, mark a closed circle at 1. Then to show all the numbers bigger than 1, shade to the right of the circle. That is the graph of the solution to the first inequality. X is less than 5 means x can be any number smaller than 5, but not 5 itself. To show 5 is not included, mark an open circle at 5. Then to show all the numbers smaller than 5, shade to the left of the circle. That is the graph of the solution to the second inequality. Nice! Now that we've solved each inequality separately and graphed their solutions on a number line, the next step is to combine these two graphs into one final graph for the compound inequality. Notice the two inequalities are joined by the word and. That means for a number to be a solution for the compound inequality, it must satisfy both inequalities at the same time. On the number line, that happens only where the two graphs overlap. The numbers shaded on both graphs are the solutions to the compound inequality. So now, we'll graph the overlap region. Let's start with the endpoints. Look at 1. Is it shaded on both graphs? Yes, it is. So 1 satisfies both inequalities. That means it is a solution. To show that, we mark a closed circle at 1. Now look at 5. Is it shaded on both graphs? No, it's not. It's an open circle on the second graph, right? That means 5 doesn't satisfy both inequalities at the same time. So it is not a solution. To show that, we mark an open circle at 5. All numbers between 1 and 5 are shaded on both graphs, right? That means they satisfy both inequalities. So they are all solutions. To show that, we shade the entire region between the two circles. This final graph shows all the numbers that satisfy both inequalities at the same time. It's the graph of the solution to the compound inequality. Therefore, our solution is all numbers between 1 and 5, including 1 but not 5. In inequality form, we can write this as 1 is less than or equal to x less than 5. This is basically a compact way to write this one. Awesome! Now let's write this in interval notation. Interval notation is just a short way to write the same solution using parentheses and brackets. We always write intervals from left to right. Since 1 is included, we start with a bracket. That's just like our closed circle. Then we write 1, followed by a comma. Next comes 5, and since it is not included, we close with a parenthesis. That's just like our open circle. That's your answer in interval notation. Therefore, for our first example, this is the solution graphically, this is the solution in inequality form, and this is the solution in interval notation. They all represent the same set of numbers. Alright, let's quickly recap the steps we followed to get here. First, we solved each inequality separately. Then, we graphed each solution on a number line. Next, we combined the two graphs into one final graph for the compound inequality. Since this one is an AND type, we looked for the overlap. And finally, we wrote that solution in inequality form and interval notation. Pretty straightforward, right? Now in this example, one graph shaded to the right and the other to the left, overlapping in the middle. But what if both inequalities shade in the same direction? Let's find out in the next example. Just like before, our first step is to solve each inequality separately. Feel free to pause the video and try solving them. For the first one, to get x by itself, divide both sides by 4. That gives us x is less than -2, right? That is the solution to the first inequality. Now for the second one, first isolate -7x by subtracting 11 from both sides. On the left, the 11's cancel out, leaving -7x. On the right, -3 minus 11 is -14. Now to get x by itself, divide both sides by -7. But remember, whenever you divide or multiply both sides of an inequality by a negative number, you must flip the inequality sign. Here, greater than or equal to flips to less than or equal to. Now on the left, the -7's cancel, leaving x. On the right, we get 2. That is the solution to the second inequality. By the way, if you'd like a detailed step-by-step lesson on solving single inequalities, including how to graph their solutions and write them in interval notation, check the link in the description. Now that we've solved both inequalities, the next step is to graph their solutions on a number line. For x is less than -2, mark an open circle at -2 to show it's not included. Then shade to the left to show all the numbers smaller than -2. For x is less than or equal to 2, mark a closed circle at 2 to show it is included. Then shade to the left to show all the numbers smaller than 2. Now look at that, both graphs shade in the same direction. Now comes the important part, combining the two graphs. Remember, since this is an n-compound inequality, for a number to be a solution, it must satisfy both inequalities at the same time. And that happens only where the graphs overlap, right? So let's start with -2. Is it shaded on both graphs? No, it's not. It's an open circle on the first graph, right? That means -2 doesn't satisfy both inequalities at the same time. So it is not a solution. To show that, mark an open circle at -2. Then, since all numbers to the left of -2 are shaded on both graphs, those numbers satisfy both inequalities, so they are the solutions to the compound inequality. To show that, we shade everything to the left of the circle. This final graph shows all the numbers that satisfy both inequalities at the same time. It's the graph of the solution to the compound inequality. Therefore, our solution is all numbers less than -2, but not -2 itself. In inequality form, you can write this as x is less than -2. Easy, right? Now, let's write this in interval notation. Remember, on the number line, the far left is -infinity, and the far right is +infinity. We always write intervals from left to right. So since our solutions go on forever to the left, we start with a parenthesis, then -infinity, followed by a comma. Remember, infinity always gets a parenthesis since it's not a specific number we can actually reach. Next comes -2, and since it is not included, we close with a parenthesis. That's your answer in interval notation. Excellent. Now, in this example and the previous one, the graphs overlapped. But what if there's no overlap at all? That's what we'll explore in the next example. As always, we start by solving each inequality separately. For the first one, start by isolating 6x, by subtracting 3 from both sides. On the right, the 3's cancel out, leaving 6x. On the left, we get 6, right? Now divide both sides by 6 to isolate x. The 6's cancel, leaving x. And 6 divided by 6 is 1. So we have 1 is greater than x, which is just the same as saying x is less than 1. That is the solution to the first inequality. The second inequality has parentheses, so our first step is to remove them using the distributive property. Distribute the 2 to both x and -1. That gives us 2x minus 2, right? Then add 2 to both sides to isolate 2x. On the left, the 2's cancel out, leaving 2x. On the right, we get 6. Finally, divide both sides by 2 to get x by itself. That gives us x is greater than 3, right? That is the solution to the second inequality. Perfect. The next step is to graph each solution on a number line. For x is less than 1, mark an open circle at 1 to show it's not included. Then shade to the left to show all the numbers smaller than 1. For x is greater than 3, mark an open circle at 3 to show it's not included. Then shade to the right to show all the numbers bigger than 3. Great, both graphs are ready. Now comes the exciting part, combining them. But look carefully. Do you see any region where they overlap? There's no overlap at all, right? That means there's no number that satisfies both inequalities at the same time. Therefore, this compound inequality has no solution. We don't shade anything on the number line. We just write no solution or use the empty set symbol to show that there's no solution. To sum it up, for an and compound inequality, if the two graphs overlap, the solution is the overlap region. But if there's no overlap, then there's no solution. Makes sense, right? Awesome. Now let's look at a special, more compact type of and compound inequality, the double inequality. The best part, it's often even easier to solve. This compact form is actually a shortcut for writing two inequalities at once. It's the exact same thing as 8 is less than 3x plus 2 and 3x plus 2 is less than or equal to 17. So a double inequality is just an and compound inequality in disguise. Now we can either solve the long form like we did in the previous examples, or solve the compact form directly. Both methods give the same answer, but let's see the faster way, solving the compact form directly. The goal is still the same, get x by itself, but this time in the middle. The golden rule for solving any double inequality is that, whatever you do to the middle, you must do to the left and the right sides to keep everything balanced. First, we need to isolate 3x in the middle. To do that, we subtract 2 from all three parts. Now in the middle, the 2's cancel out, leaving 3x. On the left, we get 6. On the right, we get 15. Next, divide all three parts by 3 to get x by itself. In the middle, the 3's cancel, leaving just x. On the left, we get 2. On the right, we get 5. That is it. That's the solution to the double inequality. X can be any number between 2 and 5, including 5, but not 2. Great. Now let's graph this solution on a number line. Since 2 is not included, mark an open circle at 2. Since 5 is included, mark a closed circle at 5. Then shade the region between the two circles to show all numbers between 2 and 5. That's your solution on the number line. Nice. Now let's write it in interval notation. Remember, we always write intervals from left to right. Since 2 is not included, we start with a parenthesis. Then we write 2, followed by a comma. Next comes 5, and since it is included, we close with a bracket. That is your answer in interval notation. Pretty straightforward, right? That's the beauty of a double inequality. You can solve it all at once and get the entire solution in one neat statement. If you solve the long form the way we did in the previous examples, you'll get the exact same answer. If you'd like, pause the video and try solving it. Then come back to check. Here is the full solution. Perfect. If this video has been helpful so far, give it a thumbs up and subscribe. It really helps the channel reach more students. Alright, let's keep going. Our next example is another double inequality, but this one is a little tricky. The variable has a negative coefficient. Just like before, our goal is to get x by itself in the middle. And remember, whatever you do to the middle, you must also do to the left and right sides. First, isolate negative 5x by adding 1 to all three parts. In the middle, the 1's cancel out, leaving negative 5x. On the left, we get negative 5. On the right, we get 10. Now, to get x by itself, divide all three parts by negative 5. But remember, because we are dividing by a negative, we must flip both inequality signs. So the less than or equal to becomes greater than or equal to, and the less than becomes greater than. Now in the middle, the negative 5's cancel, leaving just x. On the left, we get 1. On the right, we get negative 2. But wait, that's written backward, right? Take a careful look. It's written from largest to smallest, with 1 on the left and -2 on the right. But it should be from smallest to largest. -2 should be on the left and 1 should be on the right. To fix this, we can just reverse the entire thing around. That means we switch the positions of the numbers. We also move the inequality signs with their numbers, but we must flip their direction to keep the meaning the same. So the greater than moves with -2 and becomes less than. And the greater than or equal to moves with 1 and becomes less than or equal to. Now everything is written correctly and makes sense. Double inequalities are always written this way, from smallest to largest, and they always use less than or equal to signs. That's your final answer in inequality form. X can be any number between -2 and 1, including 1, but not -2. Excellent. Now let's graph this on a number line. Since -2 is not included, mark an open circle at -2. Since 1 is included, mark a closed circle at 1. Then shade everything in between. That's your solution on the number line. In interval notation, it's written from -2 to 1 with a parenthesis at -2 since it is not included and a bracket at 1 since it is included. And just like before, if you split the compact form into 2 single inequalities and solve, you'll get the exact same answer. Here's the full solution for you to check your work. If you have any questions, feel free to drop them in the comments. I would love to help you out. Awesome! Now that we've mastered and compound inequalities in all their forms, let's switch gears to OR compound inequalities. Just like with AND compound inequalities, the first step is to solve each inequality separately. Let's start with the first one. First, isolate 2x by subtracting 3 from both sides. On the left, the 3's cancel out, leaving 2x. On the right, we get -4. Now divide both sides by 2 to get x by itself. That gives us x is less than -2, right? That is the solution to the first inequality. Now for the second one, first isolate -3x by subtracting 1 from both sides. On the right, the 1's cancel out, leaving -3x. On the left, we get -6. Then divide both sides by -3 to get x by itself. Remember, dividing by a negative flips the inequality sign. Now on the right, the -3's cancel, leaving x. On the left, we get 2. So we have 2 is less than or equal to x, which is just the same as x is greater than or equal to 2, right? That is the solution to the second inequality. Great! The next step is to graph each solution on a number line. For x is less than -2, mark an open circle at -2 to show it's not included. Then shade to the left to show all the numbers smaller than -2. For x is greater than or equal to 2, mark a closed circle at 2 to show it's included. Then shade to the right to show all the numbers bigger than 2. Makes sense so far, right? The next step is combining the two graphs into one final graph. Notice the two inequalities are joined by the word OR. Remember, with AND, for a number to be a solution, it must satisfy both inequalities at the same time, right? But with OR, it just needs to satisfy one of the inequalities, not both. If it happens to satisfy both, that's fine too. So here, all numbers less than -2 satisfy the first inequality, so they are solutions. All numbers greater than or equal to 2 satisfy the second inequality, so they are solutions too. -2 and all numbers between -2 and 2 are not solutions because they don't satisfy either inequality. So our final graph is simply both original graphs combined. It shows all numbers that satisfy at least one of the inequalities. Therefore, the solution is all numbers less than -2 or all numbers greater than or equal to 2. In inequality form, we can write this as x is less than -2 or x is greater than or equal to 2. In this example, this matches the one we already have here. Perfect. Now let's write it in interval notation. Since our solution has two separate parts, we need two intervals. For the left part, since the solutions go on forever to the left, we start with a parenthesis, then -infinity, followed by a comma. Next comes -2, and since it's not included, we close with a parenthesis. For the right part, since 2 is included, we start with a bracket. Then we write 2, followed by a comma. Next comes positive infinity, since the solutions go on forever to the right, and infinity always gets a parenthesis. Finally, we join the two intervals with a union symbol, which is just a math way of saying OR. That's your answer in interval notation. Awesome! Now let's think about this. What if this had been an AND inequality instead? For an AND inequality, a number must satisfy both inequalities at the same time, right? And that happens only where the graphs overlap. But here, there's no overlap at all. That means there's no number that satisfies both inequalities at the same time. So, an AND version would have no solution. To sum it up, when the graphs of the two inequalities shade in opposite directions with no overlap, for an OR compound inequality, the solution is simply the union of the two graphs. But for an AND compound inequality, there's no solution. All right, in this example, the graphs shaded in opposite directions with no overlap. But what if both inequalities shade in the same direction? Let's find out in the next example. As always, we start by solving each inequality separately. For the first one, we have variables on both sides. So we'll begin by collecting them on one side of the inequality. Let's collect them on the left by subtracting 5x from both sides. On the left, 9x minus 5x gives us 4x. On the right, the 5x's cancel out, leaving just 4. Now isolate 4x by adding 8 to both sides. On the left, the 8's cancel out, leaving 4x. On the right, we get 12. Finally, divide both sides by 4 to isolate x. That gives us x is greater than or equal to 3, right? That is the solution to the first inequality. Now for the second one, to get x by itself, divide both sides by -6. Remember, dividing by a negative flips the inequality sign. So the solution to the second inequality is x is greater than 0, right? Excellent. The next step is to graph each solution on a number line. For x is greater than or equal to 3, mark a closed circle at 3 to show it's included. Then shade to the right to show all numbers greater than 3. For x is greater than 0, mark an open circle at 0 to show it's not included. Then shade to the right to show all numbers greater than 0. Now look at that, both graphs shade in the same direction. Now comes the important part, combining the two graphs. Remember, since this is an OR compound inequality, for a number to be a solution, it just needs to satisfy one of the inequalities. All numbers greater than 0 satisfy the second inequality. So they are solutions. And notice that the first graph is completely inside the second one. Every number that is 3 or greater is automatically also greater than 0, right? That means the greater than 0 solution already includes every number from both inequalities. So our final solution is simply all numbers greater than 0, but not 0 itself. In inequality form, we write this as x is greater than 0. In interval notation, it's written from 0 to positive infinity with parentheses at both ends. Makes sense, right? Now what if this were an AND inequality instead? For an AND inequality, the solution is the overlap region, right? So where do these two graphs overlap? They overlap starting at 3 and going to the right. So for an AND version, the solution would be all numbers greater than or equal to 3. To sum it up, when the graphs of the two inequalities shade in the same direction, for an OR compound inequality, the solution is the larger shaded region, that's the union. But for an AND compound inequality, the solution is the smaller shaded region, that's the overlap. Makes sense, right? All right. Now let's look at the case where the graphs of two inequalities shade in opposite directions and overlap. In this situation, the solution for an OR compound inequality is all real numbers. Feel free to pause the video and give it a try. This is our last example. Start by solving each inequality separately. For the first one, to get x by itself, multiply both sides by the reciprocal of -1/3, which is -3, right? And remember, when multiplying by a negative, you must flip the inequality sign. Now on the left, the 3's cancel, the negatives make a positive, and we're left with just x. On the right, -2 times -3 is 6. So the solution to the first inequality is x is greater than 6. Now for the second one, first isolate the variable term by adding 1 to both sides. On the right, the ones cancel, leaving 4/5 x. On the left, we get 8. Now to isolate x, multiply both sides by the reciprocal of 4/5, which is 5/4, right? On the right, the fractions cancel, leaving x. On the left, 8 divided by 4 is 2, and 5 times 2 is 10. So we have 10 is greater than x, which is the same as x is less than 10, right? That is the solution to the second inequality. Great. Now graph both solutions on a number line. For x is greater than 6, mark an open circle at 6 to show it's not included, then shade to the right to show all numbers greater than 6. For x is less than 10, mark an open circle at 10 to show it's not included, then shade to the left to show all numbers smaller than 10. Now comes the exciting part, combining the two graphs. Since this is an or compound inequality, a number just needs to satisfy one of the inequalities to be a solution, right? All numbers greater than 6 satisfy the first inequality, so they are solutions, and that includes 10. All numbers less than 10 satisfy the second inequality, so they are also solutions, and that includes 6. This means every number you can think of satisfies at least one of the inequalities. The two graphs together cover the entire number line. So the solution is all real numbers. In inequality form, we can write this as -infinity less than x less than +infinity, which means x can be any real number. In interval notation, that's written from -infinity to +infinity, with parentheses at both ends. That shows the entire number line. You can also simply write your answer as all real numbers. Awesome! Now what if this had been an and inequality instead? For an and inequality, the solution is the overlap region, right? So where do these graphs overlap? Between 6 and 10, right? So for an and version, the solution would be all numbers between 6 and 10, but not including 6 and 10, because 6 is an open circle on the first, and 10 is an open circle on the second graph. To sum it up, when the graphs of the two inequalities shade in opposite directions and overlap, for an or compound inequality, the solution is all real numbers. But for an and compound inequality, the solution is only the overlap region. Makes sense, right? Great! To learn how to solve absolute value equations, click the video on the screen. You can also find the link in the description or the first comment. And if this lesson helped you, give it a thumbs up and subscribe.